Welcome. So today I'm going to start the first intermediate, that is carbohydrates. So before we discuss about of that carbohydrates, how it is reactives, we have to know that its structures. This its structure says that how it is reactivity and why it is reactivity. Okay, so first we will discuss on the structure of carbohydrates. So you see that we generally write that carbohydrates, that is C positive. So positive means that electron deficient. This positive shows that electron deficient is there. Now whenever that carbohydrates, we will see that its shape is, it has the shape of trigonal planar. That is like that carbohydrates. Let's say here we have that n atoms A, and here an atom B, and here an atom C, and here we have that positive charge. So this is a structure of the shape of the carbohydrates, and this is in the planar, that is trigonal planar. Its shape is trigonal planar. And what is the angle for the trigonal planar? That is, we know that for angle for the trigonal planar is 120 degree. It means that in between the two bonds the angle is 120 degree. Here also 120 degree. So for a carbohydrates, what it needed, the angle is 120 degree. Okay, so this has to be very clear that for a carbohydrates the angle needed is 120 degree. For tetrahedral shape, that angle is 109 degree. Let's say we have that carbon atoms like this, carbon here, and let's say here hydrogens, that's the tetrahedral shape, here hydrogens. This is the tetrahedral shape. This methane has the shape of tetrahedral, and here that angle is 109.5 degree something. Okay, so that is 109 degree. So whenever you discuss about of that any carbon atoms with carbon atoms has that for valence electron, so whenever it fill the octets, and it's generally make the tetrahedral shapes where that angle needed is 109.5 degree. But whenever you talk about of that carbohydrates, so for that it has the shape of trigonal planar, and its angle, the angle needed for the trigonal planar is 120 degree. That is in this shape, the bond, the angle between the two bonds is 120 degree. So this should be very clear that what the angle needed for a carbohydrates. Carbohydrate is a very different things, and whenever you're making that carbons with have that or like it have the octet field, on that time the angle is 109 degree, and that on the time that is a tetrahedral shapes, and angle is 109 degree. So we know that this carbohydrates, how it forms this carbohydrates. Let's say we have these kinds of atoms here, this carbon here A and here B. This is in the planar. See, this is not planar, this is not planar, because one is above. This shows that above sides, this is in above, and this shows that this is in down sides. It means that this is not planar, but this, the trigonal planar, this carbohydrate is in planar. Okay, So let's say if that atoms is like this, let's say D, and let's say C, and let's say here we have that uh, D, or like let me say that this is living group. Okay, for this, that how will you how that bonded is carbons has that atomic number is 6. It means that it has that 1s2 2s2 1s2 2s2 and 2p2. So the valence electrons are this 2s2 and 2p2. The valence electron is 2s2 and 2p2. And if I make that orbitals there, let's say this is 2s orbitals, and let's say this is 2p orbitals. Okay, now that electrons, what it has that 2s2 and 2p2, so 2s2 and 2p2, and this is at the ground state. Now at excited state, actually that it will make the bond at excited state. So at excited state, how it will be? So these electrons, one electrons will shift from here to here. That is going to be that this is going to be like this, and this is shifted to here. So this is the 2s orbitals and the 2p orbitals. So this is at the excited state. Now when it will make bond at the excited states, because when it go to the excited state, then it will make the bond. Bond formations, bond formed at excited state. It means that this is this carbon atoms, this is happened at excited state. It means that A, B, C and living groups are here. So let's say that here we have that A, and here we have that B, and here we have that C, and due to that this will make bonds. Okay, because whenever we say that this bond, it means that this bond represents this and this. Okay, the two electrons make the bond. This is the two electrons. Or sometimes we see that this bond means positive and negative. Okay, so please note that whenever you say bond means two electrons are there, whenever bond means positive and negative charge is there, then that will make this bond. So this has the bond because two electrons, and here also two and here also two electrons, and this is the living groups. Or it's better to take that examples. Let's say we have that carbons here, let's say here we have that CH3, here we have that CH3, and here we have that CH3, and let's say here we have that chlorines. So this is for that CH3, this is for that CH3, and this is for that CH3. Now whenever here that since this is carbon and this carbon, and the electron difference between this carbon is almost nearly same, it means that this bond will be there somehow here in the middle of this bond. Okay, and this carbon and this carbon electron difference is nearly same, so this is because same carbons, so that electrons are stayed in the middle. Here also the same things, but in case of chlorines and carbons, we see that for carbon and chlorines, so electronegativity, if I talk, then this chlorine has very high amount electronegativity than the carbon, because this is the halogens groups. Okay. So since this is the more electronegativity, so more electronegativity atoms, what they will do, that they abstract electrons towards itself. It means that this bond will not lie in the middle, they lie nearly to the chlorine atoms, because this will obstruct electrons towards itself. So that two bonded electrons will lie somewhere near to the chlorines. So that it means that this electron density is shifted towards the chlorine atoms, because chlorine is the electronegativity atoms and carbon is the less electronegativity atoms. It has, let's say, little delta positive charge, and let's say it has little delta negative charge. It means that more electrons are, although bond is there, but the electron densities are more towards the chlorines. Okay, so now this is the leaving groups. So what that it will leaves, and whenever it will leaves, it will take the two electrons and it will leave. So let's say here we have that chlorines, and due to this electrons is there, but these are more lies towards the chlorine atoms. So whenever it will leaves, it will take these electrons and it will leave. So after that it will leaves, then what will happen? So these chlorine atoms take the electrons. This one is for the this one atom is from the chlorines, or it's this is from the chlorine, and this one electron is from the carbon. And what the chlorine did, that it will take the two electrons. It means that it takes the electrons from the carbon and it leaves. Okay, or I can write here. Let's say this is the atoms, the atom of chlorines, carbons. Here it have, and these are the atoms of the carbons. So this CH3, and this is the for this carbons, and this is this carbons. And whenever this is for this carbons, but due to that electronegativity of the due to that chlorine has more electronegativity, the carbon electrons also shifted more towards the chlorine atoms. And let's say that it is the electrons of the chlorines. So what the chlorine did, that it take the electrons of the carbon and its own electrons and it leaves. It means that it takes the electron from the carbon also. So if that carbon lost one electrons, it means that this carbon get positive charge. So now what will its structure will be? Carbon here, here CH3 is there, here CH3 is there, and since this chloride take that two electrons and leave, here it will get the positive charge. Okay. So what it will happen, that if you if I represents here, after chlorine leaves, then what that orbitals will be? So this is the carbon's atoms. So this chlorine take the two electrons and it left. It means that here we have this bonded. Here we have that CH3 is there. Here also CH3 is there. Here also CH3 is there. But this chlorine has left by taking these two electrons. So here we have only this is there. So you see that what happened, that this chlorine take these two electrons and it left. It means that this is the 2s orbitals and this is the 2p orbitals. So these 2p orbitals, these orbitals get vacant. So that's what we see, that whenever you discuss about of that carbocations, it has that vacant free orbitals, because these two orbitals, although it has filled, but one orbitals get vacant when that leaving groups did, or when carbocations pour. Okay, that's why we see that for carbocations it has that vacant free orbitals. Okay, so from here if you says that we can write some points. So from here what we notice about of that carbocations. So whenever you take that, whenever the leaving group is there, count the electrons. How many electrons are there? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. It means that octet is filled. But when that leaving groups left, how many electrons are there? 1, 2, 3, 4, 5, 6. It means that octet is incomplete. Two more electrons are needed to fill the octets. So carbocation case, what happened that its electrons are less than octet. Okay, so I can hear that octet incomplete. Okay, so from here we notice that this whenever the tetrahedral carbon is there, then on that time it has that 8 electrons. But when that it formed the carbocations, what happened that it have only 6 electrons. 1, 2, 3, 4, 5, 6. It means that two more electrons is needed to complete the octet. Okay, so this is octet incomplete, and what it needed, that it need two more electrons to complete its octet. It means that it need electrons. Okay, if it need electrons means it loves the electrons, and we know that electrophile, what it says, phile means love, and electrons means this is electron loss. That's why carbocation is called that electron deficient, or we can say that it is electrophile. Okay, and since that it need two more electrons to complete its octet, so this is highly reactive. Highly reactive, highly reactive to get octet. So this is highly reactive because it need two more electrons to complete octet. When it get octet, then that is unreactive, so it need two electrons to get octet completions, because it wants to stay in the stable forms, and its stable forms will comes when it will fill octet. Okay, so it need two more electrons, so it wants the electrons. It means that it has to be a reactive. And what we say that about of the carbocations, it is octet incomplete, it is electron deficient, it is highly reactive. Another is that it has the vacant free orbitals. Vacant free orbitals. Okay, that's what we see here. It has the vacant p orbitals. And what things we see, that although it has vacant p orbitals, whenever you count that electrons, all are pair. 1, 2, 3, 4, 5, 6. It means that all electrons are pair here. It have paired electrons. It means that it is diamagnetic. And whenever it is diamagnetic, it means it have that no unpaired electrons. No unpaired electrons. It means that it is ESR inactive, because for ESR to active it has to have at least one unpaired electron, but here all are paired. It means that this is ESR inactive. So these are the some things what we have seen by looking the carbocations orbitals. Okay. Now we will look about of that on which case that carbocations will stable. So this is the carbocations. Let's say this is the carbocations. Let's say here we have A, B, and C. This is the carbocations. And to get stabilize this carbocations, this is highly reactive. This is reactive. Let's say this is reactive, and I want to stable this carbocations. Then how I will stable it? I have to give some electrons to it. Then it will get stabilized. Okay. So what I write that to stabilize carbocations, uh, we will give electrons to it so that octet will complete, and at the octet means that it will give it will be unreactive, because octet is the stable state. Octet is stable state for this carbons like hydrogens, whatever that this carbon atoms, nitrogen, oxygen, they have that octet state. They need the octet for the stable. Octet is stable for carbocations. Okay. So it has to give the electrons to stable this carbocations. So electron means which will give electrons. That means that something like nucleophile. So nucleus means that is that they lobes that this positive charge. So if you give that nucleus, then nucleophile, they will get stabilized. So they will get that electrons. Nucleophile means which give the electrons. Nucleophiles means donate electrons. Okay, so to get the stable the carbocations, they need the electrons. So let's say we have this carbocations, and if you have that hydrogen is present here, hydrogen is present here, and hydrogen is present here, and let's say here we have that carbocations, or this carbocations here, H is there, H and H is there. Okay, and this has the positive charge. So here what happened that the electron donating means this carbocations will stable if it get the electrons. Now if we have the three hydrogens around it, then what happened that they will very less, they will donate the electrons. So hydrogens donate very less electrons. But again, if we have that instead of hydrogen, let's I replace one CH3 group, and here we have that hydrogen, here we have that hydrogens. In this case, what we know that this CH3 groups, it donate electrons through sigma bond. It means that this is, we know that this is inductive effect. Okay, so since this is donate electrons through sigma bonds, means it donating somehow some electrons. So here that hydrogen is not donating. Here that instead of hydrogens, we have that CH3 groups and it donating electrons. It means that this carbocation get more stabilized from this. Okay. Now similarly, again now if you replace this carbocations with one more CH3, and here we have that hydrogens. Now this both will donate electrons, this and this and this and this. It means that here this carbocation get more stabilized than this. Okay, now if you have that these carbocations, let's say here also we have that CH3, here also we have that CH3, and here also we have that CH3. In this case, all the three carbons are donating electrons to these carbocations. It means that this carbocation get more stabilized. It means if I write this A, and if I write this B, if I write C, and if I write D, So what will that stability of carbocations will be? That first is D, then we have C, then we have B, then we have that A. So what we see that this type of carbocations where that three carbon atoms, that this is called that 3-degree carbocations. And whenever two carbons are there, then that we are going to say that 2-degree carbocations. And whenever one CH3 group is there, then we say that 1-degree carbocations. Okay, so from here also we say that 3-degree carbocation is more stable than 2-degree carbocations, then the 1-degree carbocations. Then that simply this is simply that CH3 carbocations. Okay, so this is the stability of carbocations or order of table of carbocations. Okay, this is about of that stability of the carbocation. So what we say that first 3-degree, then 2-degree, then 1-degree, then simply that CH3 carbocations. Okay, so this is about of the stability of carbocations. Also like you know that if in the carbocations, let's say this is the carbocations is there. Now let's say here we have that these groups, and here we have that this CH3 groups is there, and let's say here we have that A and B. In other case, let's say the carbocations is there, and let's say here we have that OCH3 or like OCH3, right? Here we have that OH groups, and let's say here B, and let's say this is A. And these carbocations, let's say here we have that mm, what groups? Let's say I like that let's say this type of group is there. Okay, and here let's say B is there, and here is A, and let's say this is the carbocations, and here we have that B, and here we have that A, and let's say here some aromatic ring is there. Okay, now compare the stability of carbocations. Compare the stability of carbocations. So remember that carbocation has that vacant p orbital is there, and it need two more electrons to get stabilized. So it will stabilize when it will get electrons. How much it will get electrons, that much it will get more stable. Okay, that's what we have seen, that it has the vacant p orbitals and it need that two more electrons to complete its octets. So it depends on that where it is getting more electrons. In that case, the carbocation will get more stabilized. Now in this case, what we have seen that here that CH3. Okay, so you know that hyperconjugation effect. It means that here if we have this carbon, hydrogens, and this hydrogen. So this what will do that no bond. Hyperconjugation means that no bond effect. It means that this will donate electrons. So that hyperconjugation effect that I will discuss clearly in the later class. So it will do that 3 alpha hydrogen is there, 3 alpha hydrogens. So it means that hyperconjugation is here, hyperconjugation, that is 3 alpha hydrogens. Okay, now in this case this has that lone pair. It means that it will donate this electrons toward itself. It means that this is have that blossom effect. It has blossom effect. Okay, because this has the lone pair, it is donating lone pairs towards its. Here it donating from this sigma bonds. This sigma bonds is donating towards itself. And what you know that this CH, since it is a sigma bond is a strong bond, so donating electrons from this is not that easy as compared to here, because it is that freely available uh, lone pair electrons, so that it can easily donate to here. Okay, so that is called the blossom effect. And now here only that here this carbon is there and only one hydrogen is there where it can donates. Okay, this it can't donate, this will not show the hyperconjugation effect, means that only one alpha hydrogen is there for hyperconjugations, and rest that it will do that. This is also have that inductive effect, plus it is also have that inductive effect. It means that it will donate one alpha hydrogen, here it will donate the three alpha hydrogens. Means that one sigma bonds from here also it can donate here. With that it also have that inductive effect, means these two groups, due to this also that little bit electrons is donated to this carbocations. Here that through it can donate from here, it can donate from here, it can donate from here. So three alpha hydrogen is there for donating electrons to this carbocations. And now in this case this is that aromatic systems. And this aromatic systems, what it will do that uh, okay, so here what we see that this aromatic systems it will donate electrons. Okay, that we will discuss clearly in the next class. So here that aromatic, it means it is somehow like this carbocations is stabilized by the aromatic systems. It means that this carbocations getting it will donate. Okay, so write that carbocation is stabilized by aromatic systems. So from here what we see that, let's say this is A, and let's say this is B, let's say this is C, let's say this is D. So from this where the carbocation will get more stabilized. So another is, let's say that anti-aromatic systems. So that the detailed things we will discuss later. So now for the time being, what I will say that the carbocations stability will be more if it is getting that carbocation stabilized by the carbocation. It means that first aromatic will give more stable if it is aromatic. Okay, so I don't think this picture is right. uh, that if the carbocation getting aromatic, then that will get more stable, then it will have that it is getting the Blossom effect. Okay, Blossom effect means that pre electrons is this electron is getting from here, so here it will get more electrons, that's why this is get more stable. It means that where it will get more electrons, on that time that will the carbocation will get more stabilized, because carbocation need the electrons. Okay, so Blossom effects. Then what we have that here it will take getting electrons from this bonded CH atoms. So here that hyperconjugations will come. Okay, if you're getting the electrons from the hyperconjugations. Why what I say that, because you see that CH atoms, because the electronegativity of the carbon is more than hydrogen, so that electrons are uh, less bondly the electrons are less bonded, so this can easily donates. Okay, if because this bond is not so strong, so they can easily donate this bonded electrons. Okay, so that's why, so that hyperconjugation effect. So first is that aromatic, then it getting from plus M effect, and then that hyperconjugation effect. Then we have that inductive effect. Then we have that anti-aromatic systems. Anti-aromatic systems. Okay, so this is the how that carbohydrates will get more stable carbohydrates. This type of examples will take good examples in the coming classes. Okay, so for time being, please note that carbohydrates will get more stables if it getting that aromatics and it is getting electron from plus M effect and hyperconjugation, then inductive, then anti-aromatic systems. Okay, and very unstable, where the carbohydrates will get more unstable. Carbohydrates is unstable, means that we never prefer this, means that is very unstable, means that type of things we will not get. That is, let's say we have that this aromatic systems, this benzene ring, and here suppose we have that positive charge. It means that this type of things is very unstable. Reason is that what you see here, that it is in the conjugations, and here we are doing that back and p orbitals. So this it will not get these electrons from this, because this benzene ring is these electrons are involved in the aromatics, they are in the conjugation, so it will never give electrons to this carbohydrates. Okay, and these carbohydrates need electrons, but this will never give this electron because they are in the conjugations and they are in the aromatic systems. So this type of things we will never get it. Okay, this is very unstable. Okay, so this is the, or you can write that carbohydrate, this is sp2 hybridized, sp2 hybridization. Because what I see that these electrons, these bonded electrons, they are busy in conjugations. And why they are busy? Because they are getting aromatics, and aromatic is very stable, so they will never give electrons to these vacant free orbitals. And they, if they give the electrons to these vacant orbitals, they get anaromatics, and it will never go to aromatic to a anaromatic, because anaromatic is a very stable. Okay, so it will very unstable, so it will never go to the anti-aromatics. Okay, so this is very unstable, so these things we never form. Another is that if we have this type of carbons, hydrogen is there, and let's say here that some atom is there, let's say here we have that positive charge. It means that carbohydrate sp2 hybridized. So these things also we will never see. That reason is that here we have this carbocation has that vacant p orbitals. Okay, and this is that at sp2 hybridized, and it means carbocation means it need electrons. And where from it get the electrons? Because this has already there are pi bonds, one is sigma bond, one is pi bond, here is hydrogen is there, so it is not getting any electrons from anywhere. Okay, so that's why the carbohydrate sp hybrid, these are very unstable. Or this type of bonds, carbohydrates, here let's say here we have that positive charge. So this is also the carbohydrates at sp hybridized are very unstable. So this type of things we will never form. Okay, so because it itself become an electron negative electron deficient groups, on that times you are forming a again electron deficient, means that will be never happen. Very unstable. Okay, very unstable, so never form this type of carbohydrates. Now going to that one more interesting things, that is, let's say that cyclopropane ring. This is very important, very interesting things, that cyclopropane ring. how this cyclopropane ring means that three member rings. Okay, this is three membered ring, and what it has that its electrons is like this. That p orbitals are that bonded p orbital, means that p orbitals are in this bonded structure will be there. Okay, so the cyclopropane ring is somehow it is like this. So what we see that the p orbitals, they are bonded with each other, this p orbital and this p orbitals, but they are in the bent structure, means they are not in the like this straight, they are the bent like this. Okay, means that if they are bended, means that the it has that more expanded electron density is there. What I am saying that here that proper orientations is there, but when they have this bended, means that some electrons are freely available from here, but here since they have the proper that orbital, the proper they are oriented, it means that these two electrons are very stable. But in this case these two electrons are not so stable and they are freely available, they are available to donate, means that what I might want to say that if anything it has that perfect they have that this bonding they, let's say they have the two electrons, but another thing is, let's say it is like this, like in a bended manner, it means that two electrons are there, means that orbitals are not bonded in a proper orientation. It means that with the electrons they will bond, that electrons are unstable, and if these are unstable then they can easily donate, because everybody wants to get stable. Okay, so here that electrons are, what we say that here expanded electrons is there, expanded electron density. Okay, or what we say that here that bent overlapping. So due to this band overlapping, they have that expanded electron density. And now, if this type of is there, let's say this cycle, let's say here you have that carbocations. Let's say here some group is there, and this is the carbocations. And let's say that here we have this cyclopropane ring. It means that it has that this band orbitals. So due to this band orbitals, these electrons are not so stable, and what that actually happened that since they are expanded electron density, expanded electrons are there, so they can easily give electrons to this. It means that it has, whenever carbocation means, understand that vacant p orbital is there. Okay, so these electrons from here they can easily donate to here, they can easily donate to here. It means that in this case the carbocations get more electrons from this bent orbitals, so this carbocation get more stabilized. Okay, so that's what we seen here, that whenever we have that bent orbital, this it means the expanded electron density is there, means carbocations get I can write cyclopropane ring donate more electrons to carbocations than normal bonding orbitals. Okay, so that what I mean that carbocation get more stabilized, so carbocation get more stabilized if it have cyclopropane. Okay, so these are the interesting things about of that cyclopropane rings when it have that cyclopropane ring, if it is in the if it is present near to the carbocations. But the note is that the cyclopropane has that two orientation, means that here what we see that this is the single bond, and single bond through rotations is possible. So if that cyclopropane ring is present towards the carbocations, this orientations of this cyclopropane ring can be two ways. One is it can be oriented in perpendicular to, that is why I can say that perpendicular conformations with respect to carbocations, or another is bisected conformations with respect to carbocations. So there is a two orientations, two types of orientations is possible for the cyclopropane ring. So perpendicular in the sense, let's say we have this carbocations here, and this cyclopropane ring is this manner. Okay, and let's say the bisected means carbocation is here, and let's say that is in this manner. Okay, so here that carbocation means it has that vacant p orbitals is there. Here also vacant p orbital is there. So what we seen that whenever it is in the perpendicular conformations, it means it has that these bent orbitals. So they will not able to donate this electrons, this expanded electrons, they will not able to donate to these p orbitals. This will go to here, this will go to here. So this is remaining unfilled, means that the proper donations of electrons to the carbocation is not possible if it is a perpendicular conformations. But in this case, what we see in here, so it can donate these electrons to this. So here, if it is a perpendicular conformations with respect to carbocations, then the electrons cannot be donated. The good amount of donations, good amount of electron donation to carbocation is not possible if this cyclopropane ring is in the perpendicular conformations. It means that I can write here if perpendicular conformations of cyclopropane with respect to carbocation, then electron donations to carbocation is not possible. Reason is that the orientations is not matching. It means that this is going to electrons like this directions, but in this that it able to donate the electrons more to this carbons. Here that more electron donations to carbocation is possible. So now the questions will come that since this is a single bonds, so the rotations can possible. It means that we can bring these perpendicular conformations to that bisected conformation. But the problem is what, that if it is rotate, then it needs that 133.7 kilocalorie per mole. This amount of energy is needed to rotate that, and it is here, and this amount of energy it can't get, so it will not rotate to that bisected conformations. So it will remain in a perpendicular conformations, and if it is remain in a perpendicular conformations, then it that electron donations to the carbon is not, so not good amount is possible. So this is become that unstable carbocation, and here it will become the stable carbocations. Okay, so in the previous class, in next class we will discuss the applications of this cyclopropane ring if it is present near to the carbocations. Okay, so today up to this we will discuss more in the next class. Thank you.